Hello, everyone. Thank you for joining my talk. In this talk, I will talk about distributed algorithms for dense subgraph detection and low Outdegree orientation. This is a joint work with Sinha Su at Boston College. Given in the dense subgraph problem, given a subgraph H, the density of H is defined to be the ratio between the number of edges and the number of vertices in H. And the objective is to find the subgraph with the maximum density, D stars. This problem has multiple applications. For example, in correlation mining, where vertices correspond to entities and edges correspond to heavy correlations. The densest subgraph corresponds to certain groups with high correlation. The densest subgraph problem also has other applications, for example, fraud detection, bioinformatics, community detection, and story identification in social networks. The nice things about this formulation is that even though there are exponentially many subgraphs, the densest subgraph problem admits polynomial time exact algorithms based on max flow or linear programming. It also admits fast greedy approximation algorithms. The problem has also been extensively studied in the streaming and dynamic setting, the massive parallel setting, and distributed settings. In this work, we mainly consider the local model and the conjecture model. In the local model, we are given an underlying graph, and in each synchronous route, each vertex can talk to its neighbor and perform some local computation and move on to the next route. And the complexity is measured in terms of the number of routes used by the algorithm. The conjecture model is basically the same as the local model with an extra restriction that the message size that is exchanged between any two neighbors in a route is restricted to log n bits. And for this problem, at the end of the algorithm, each vertex B will output 1 bit to indicate whether or not it is in the output subgraph. Okay, so for example, in this graph, at the end of the algorithm, the vertices in the click of size 4 should output 1 because that click is the densest subgraph in this given graph. Okay, the other two vertices should output 0. The bad news is that any constant approximation requires order diameter routes in the local model. So there is no non-trivial algorithm for this problem because if you are willing to spend diameter route, one node can collect the entire graph and solve the problem exactly. Well, to see this, consider the following scenario. On the left-hand side, you have one click, okay? And it is attached to a path of length diameter. And on the right-hand side, you may have nothing or you may have a much bigger click, okay? So in the first case, at the end of the algorithm, the click on the left should output 1 because that's the densest subgraph. On the second case, in the second case, only the right click should output 1 because it is the densest subgraph. Okay, but there's no way for the vertices in the left click to figure out which case the input belongs to. Okay, without spending diameter routes to figure out what is on the other side of the graph. Okay, so then we have to look into a slightly different formulation. So we consider the following parameterized version of the problem. Given a global parameter D that is known to every vertex in the graph, we want to output a subgraph with density at least 1 minus epsilon d, okay? And if d is smaller or equal than to d star, which is the maximum density of the graph, then the output must be non-empty, okay? If d is larger than d star, then we are allowed to output an empty subgraph. So our main result is a log n over epsilon route deterministic algorithm in the local model. We also show that any randomized algorithms with constant success probability that is high enough must use 1 over epsilon routes. And therefore, there's a natural open question whether or not the log n factor is necessary in either the upper bound or the lower bound. Okay, so the main idea for our algorithm is the following observation. Dense subgraphs are well connected and therefore they have low diameter approximations. Okay, so what does that mean? First, we look into the following concept called low diameter decomposition. In this decomposition, we are guaranteed that the graph can be decomposed into disjoint components, and each of the components has diameter at most log n over epsilon. Okay, and the number of intercomponent edges, the edges that going from one component to another, is at most epsilon times the total number of edges. Okay, so let's prove by contradiction. Okay, so consider any subgraph H. And first we applied the low diameter decomposition to H to obtain low diameter components H1, H2 up to HK, for example. And suppose that all components Hi have density less than 1 minus epsilon times the density of H, okay? Then E of Hi over V of Hi is less than 1 minus epsilon times E of H over V of H. We can multiply both sides by V of H, I, and summing over I from 1 to K. This will give us that the total number of edges inside the components is smaller than 1 minus epsilon times the total number of edges in H. Well, but this is a contradiction because the decomposition promises us that there can be at most epsilon times E of H intercomponent edges. So therefore, some low diameter component Hi must have density at least 1 minus epsilon times the density of H. Okay, so let's choose the densest subgraph as H. Okay, in other words, we set H to be the densest subgraph. Now then, it's easy to, then we immediately have that the densest subgraph has a log n over epsilon diameter approximation. Now this suggests a very simple algorithm that each vertex collects its log n over epsilon neighborhood, okay? And if D is at most D stars, then some vertex must find a subgraph with density at least 1 minus epsilon times D. Okay, however, there's a catch that it is possible that no more than one vertex finds a dense subgraph. And the union of these dense subgraphs may have low density. Okay, so we want to make sure that our output consists of a union of disjoint dense subgraph. And this requires some careful symmetry breaking, which I will refer you to the paper for full details. Okay, so next we move on to the Ganges model. In this model, the previous strategy no longer works because of the message size restriction. So a node can no longer collect it log n over epsilon neighborhood without using extremely large message size. Okay. However, we show that this can still be done using log cube n over epsilon cube around n randomization. Okay. So the trick is to look at the linear programming approach. So first, we note that the densest subgraph can be modeled by a linear program. And furthermore, Charika showed that if you solve the linear program, there is a routing algorithm that obtains the exact solution for the densest subgraph problem. However, the problem is that this LP is difficult to solve in distributed settings, and in particular, the conjecture model. Okay, so instead, we look at the dual problem of the given LP. So the dual linear program for the densest subgraph problem is the low out degree orientation problem. In this problem, for every edge E with endpoints U and B, we have two variables, alpha EU and alpha EV. And we have a constraint that alpha EU plus alpha EV is greater or equal to 1. This means that we want to say that either alpha EU is 1, okay, or alpha EV is 1. So if alpha EU is 1, we orient the edge from U to V, okay, otherwise we orient the edge from V to U. We also have a second constraint that for every vertex U, the sum of alpha EU over all edges E incident to U is less than or equal to D. Okay, we call this sum the fractional orientation out degree of U. So this means that we want to orient the edges so that the maximum out degree of any vertex is bounded above by D. Okay, so one can solve this LP by using the multiplicative weights update method. We adapt the algorithm by Bahmani et al. To solve this LP in a conjecture model. So each edge E maintains a load LE. And in each iteration T, among log n over epsilon square iterations, okay, for each vertex U, let S be the set of incident edges on U corresponding to the D over 2 highest loads. Now we set the value alpha EU in the T iteration to be 2 if E is in S. And then we set LE, we update LE to be LE plus alpha EU and alpha EV in iteration T. Okay. After L iterations, the final alpha EU value will be the average of the values alpha EU over all the iterations. Okay. Now we note that this algorithm is completely local because each edge only needs to maintain its load, okay, and two variables alpha EU and alpha EV. And this also means that these variables can be exchanged using small message size. Okay, so the nice thing is that solving this LP will give us a way to find either the densest subgraph or a low out degree orientation. So in particular, if we let VLJ to be the set of nodes that are incident on at least D over 2 edges whose load is at most L in iteration J, okay, then if the parameter d is smaller than or equal to d star, then for some value L and iteration j, the graph induced by the subgraph induced by VLJ has density at least d. In reality, we don't know the value L, so we have to guess. That's why we'll obtain a subgraph with density at least 1 minus epsilon times d instead. On the other hand, if d is at least d star, okay, then the output values alpha e, u approximately satisfy the feasibility LP. That means that for every h, e is equal to uv, alpha eu plus alpha eb is at least 1. And the fractional out degree of every vertex u, okay, the sum of alpha eu is at most 1 plus epsilon times d. Now let's look into the dense subgraph problem first. We know that if d is smaller than d stars, okay, there is some subgraph induced by VLJ that has density at least d during some iteration. However, to compute the density of these subgraphs, we need to spend diameter rounds. Okay, so the naive implementation would take log cube n plus over epsilon cube plus diameter rounds. We use probabilistic low diameter decomposition to get rid of the diameter term. Okay, and so the overall algorithm only runs in log cube of n over epsilon cube rounds. Okay, so finally we move to the low out degree orientation problem. Now recall that by using multiplicative weights method, we can obtain a fractional solution to the low out degree orientation problem. That is for every h EUV, we have alpha EU plus alpha EV is at least 1, and the fractional out degree of every vertex U is at most 1 plus epsilon times d. Okay, this can be done in log square of n over epsilon square congest rounds. Now we need to route this integral solution to an actual orientation of the edges. Well, before I go into the details, we can compare our results to the previous results. This is the first 1 plus epsilon approximation to this problem in the congest model. Furthermore, it's also deterministic. It is also much faster than other 1 plus epsilon approximation algorithms in the local model. Okay, even though we are operating in a more restricted congest model. Okay, so how do we go about routing the solution? Now, the first observation is that we only need to look at the first 1 over epsilon plus log delta significant bits after the decimal points, okay, of each of the alpha values. We route the alpha values bit by bit while maintaining the invariant that alpha EU plus alpha EV is at least 1. Now, first consider the rightmost bits of alpha EU and alpha EV. Okay, if they are both 0, we are done, right? Then we can just move to the next bit that is to the left of that bit. Okay. Otherwise, there are two cases. The first case is one of the rightmost bit is 1 and another rightmost bit is 0. This case is also simple. We can also just route the 1 bit down to 0. Okay, and it's also easy to see that after this, alpha EU plus alpha EV is also at least 1. Now the tricky case is that both alpha EU and alpha EV rightmost bit are 1. Okay, so we route one of them up. Say we route alpha V up and alpha EU down, okay? So here, if we do this, we will increase the fractional out degree of some vertices, okay? So the challenge is that we want to keep the fractional out degree of every vertex U low enough, okay? So it doesn't increase too much when we do this. So now we consider different kind of orientation, okay? This is different from the original orientation problem. Now we want to orient edges such that if we want to orient edges in that fall into this category, okay, such that if U is oriented toward, if the edge UV is oriented from U to V, okay, then we route alpha EU up and alpha EV down. Now the trick is to keep the fractional out degree of U from increasing too much, is that the out degree of U must be roughly the same as the in degree of U, okay, in this orientation. And so if you look at the fractional out degree of U, but that is sum of alpha EU, then we want the number of rounded up terms is roughly the number of rounded down terms, okay? So to do this, we use directed splitting given by Gaffarietta, and their algorithms provide an orientation in a way such that the number of edge coming into V is roughly the same as the number of edges going out of V, okay? So, so then we can guarantee that the fractional out degree of every vertex doesn't increase too much at each bit scale, okay? There's a catch that the algorithm by Gaffari doesn't work in the conjecture model, so we have to make some modification so that we can run the algorithm in the conjecture model. Okay, so after we process every bit after the decimal point, every value alpha EU is either now 0 or 1, okay? And the sum, because we maintain the invariant that alpha EU plus alpha EV is larger than 1, this constraint is satisfied. Now there's another extra required analysis that the error accumulated over the bit scales is small, okay? So that is after we process all the bits after the decimal points, the fractional, okay, the sum of alpha EU is still bounded above by 1 plus order of epsilon times d, okay? And now we have an actual edge orientation where the out degree of every vertex is bounded above by 1 plus epsilon times d. All right, so thank you for tuning in for the talk.